come to the last lecture of the day, and we'll talk a little bit more about various kinds of data structures that can be instantiated as sheaves. Some of these are from engineering, some of these are from other data sciences. So we'll get some context. So we spent past lecture talking about what are sheaves. Now we're going to start talking about encoding different kinds of data structures as sheaves, building on topological models underneath. And then tomorrow we'll pick up with some computational invariance, and we'll pull it all together at the end. Okay, so the kinds of data structures that we're interested in playing with, we should address the following kinds of questions. We should ask, first of all, how can I take those data structures and put them together and turn them into sheaves? How do I sheafify? And how do I translate between sheaves and other sheaves? So this allows me to start talking about the kinds of questions that I might have where I have data formats that need to be translated or filtering in some more general fashion. And just generally speaking, what can I do with this sheaf theoretic data structure that I've got? Okay, so remind you, what is a sheaf? So a sheaf is something that allows me to translate between physical sources or physical realms of data and the data that are associated with those physical regions. So these are various open sets or simplices in a topological space. And then these are the data spaces, and I'm able to make some translation between them by taking a look at restrictions to overlaps and then inferring back to the union. So that's what a sheaf is, something that allows me to make that inference, an inferential machine. Now, what are the things that are not sheaves? Well, if I don't have some kind of consistent way to talk about translating data or unifying the data, then I end up with some kind of consistency checks being either ad hoc or not quite systematic or not fully useful, and I end up with the failure of being able to do cross-modality inference. Okay, so we'd mentioned previously this notion of flabbiness. So if I start out with vertex-weighted graphs with no further constraints at all, that gives me a sheaf. It's got a non-trivial stalk, fine, on each vertex. All the restriction maps are 0, and the resulting sheaf is flabby. Okay, and that's not a whole lot can be said about what it's doing, because it's not doing a whole lot. On the other hand, if I have edge-weighted graphs, I showed you how to do that in the previous lecture. Naturally, these things turn out to be co-sheaves, as in the data lives on the higher dimensional cells and extends down to the lower dimensional cells. Again, all the extension maps are 0, so that everything matches up. I think the appropriate co-sheaf ought to be called co-flabby. I've never heard of that term before, but I strongly suggest that people use it.
So this is new research.
This is new research. New linguistic research. So anyway, we talked a little bit about flow sheaves in the interactive session. For the benefit of those online, summary of what a flow sheaf is. You start with a directed graph, where you think of graph a little more generally as a directed hypergraph kind of thing, where I don't necessarily have to have endpoints on all of my edges. Those allow me to connect to the external world, either as inputs or as outputs. And you look at the direction of the edges to supply some information about where a commodity is flowing. So you can imagine these are amounts of water and these are pipes. So I've got 3 units of water coming in from this edge, 2 from that edge, and what flows out is got to add up to 3 plus 2, which is 5. So 1 unit goes that way, the other 4 must go this way. This is some kind of conservation law. So this can be instantiated as a sheaf once you realize that there are some constraints. Constraints being that the sum of the inputs is better equal to the sum of the outputs. Seems reasonable and is not so hard to instantiate. If you build this thing up as a sheaf, you can build it up like so. In the most general setting, you should probably use some kind of semi-ring and modules, and that all gets very nice. The reason for doing that is simply to avoid negative numbers. That's a lot of abstraction to avoid negative numbers, but it turns out to be the right abstraction. If you don't care about having negative flow values, that's fine to you. You can work with vector spaces, real numbers. So here I've got one real valued input, another real valued input, another real valued output, another real valued output, and some subspace of that set of those 4 numbers instantiating the conservation law. So typically what you'll see, if I've got actual conservation sitting right here, these, these four numbers describing what's going on at this vertex, the stalk is four-dimensional here, I could in fact really say that I'm really only assigning a certain three-dimensional subspace out of this, those that conserve the flow. Not so bad. And you end up with restriction maps that are sometimes projections. Okay, fair enough. The idea is that if I have something like this, where I've got maybe 3 units coming in, 2 units coming in, 1 unit going out, and 5 units going out, well, that seems inconsistent with the data. Or perhaps 4 units going out here, 3 units coming in, and 8 coming out, that would imply 5 units here. Again, that's inconsistent. So that would imply that I have a local section defined on everything here, with the exception of this edge. So that either says that either flow is not conserved, or there's been an error in measurement. Could be an error in measurement, could be flow, could be the wrong model. We don't know from the outset, but it certainly is not consistent. Okay, the neat thing with this is that you can, in fact, end up with different amounts of inferential ambiguity depending on how much measurement you started with. So if you start with local sections that are defined on the black edges in these 3 different instances, and you'd like to ask about extending to the red edges, sometimes there's no possible inference. This is the one we were just seeing on the previous slide. Inferring from this vertex, this number better be 4. Inferring from this vertex, it better be 5. 4 is generally not equal to 5, so that's it. In this case here, there's exactly 1 possible inference. It better be 4. And here, it's undetermined. There are many possibilities. So the process of extending sections can give you a lot of flexibility and a lot of richness in the kind of models that come out of the other end. That's kind of nice. Now,
generally, don't you have uncertainty in your measurement?
Okay.
So,
right.
in fact, on your left-hand graph, it might actually be within error bars.
It could be, yes. So you're right. If in fact I'm thinking of these as not being numbers, but rather some other kind of object, then I really might be totally fine. And in particular, good anticipation, Bayesian networks are a good way to manage this, where I would have some amount of uncertainty. Now what I have on edges are probability distributions. That sounds pretty decent. So if I start with a set of random variables, there they are, consider the set of all joint probability distributions on this, some measure spacey kind of thing. Then I've got these non-negative measures describing probability distributions that vector the integral. This is not a vector space. If I add 2 probability distributions, I do not necessarily get a probability distribution. Right? That integral additivity kind of gets in the way. All right, that seems kind of reasonable, but is what it is.
What did you just say?
I said that if you have a probability distribution and another probability distribution, if I try to add them together, I don't get a probability distribution.
Oh, so it's not adding the arguments, but it's adding the probability.
That's adding the distributions themselves, right? That is not a vector space.
No.
Definitely not. But what's kind of neat about this is that I can do other operations. In particular, if I have this large set of random variables, I can marginalize. There's a natural way to translate from n plus 1 random variables to n random variables. How? By integrating over that remaining random variable. There's a marginalization. Well, if you start doing this, if you marginalize over various other combinations of random variables, I get lots of different marginalization maps. In fact, I get one for every possible arrangement here. That suggests that, well, I've got a lot of data. In fact, it turns out this naturally gives me a co-sheaf on the complete n simplex. So let me show you what that looks like, because this is a little bit abstract. So first of all, if I've got, let's see here, I've got my notion of, let's take a look at 3 random variables. What 3 random variables do I have? x0, x1, and x2. Okay, and so what is the space of probability measures? Here it is. Here's the space of probability measures on those 3 random variables, joint probability random variables. So these are, strictly speaking, these are functions from R3, or not R3, from the Cartesian product of these guys, rather, to the real numbers, of course, non-negative real numbers, such that the integral is 0. Yeah, measurable functions of that sort. Okay, so what I can do is I can marginalize out, say, like that function says. I can marginalize out the last one. I can also marginalize out the first one, or I can marginalize out the middle one. Of course, now that I've marginalized out, I can keep going, right? I can marginalize out, in this case, just so that I've got the x1 remaining. Here, just so I get the x2 remaining. And here, that I've got just the x0 remaining. When you look at this diagram, you realize this is the attachment diagram of a complete 2-simplex. There's 0, I'll label it with the random variable in question, x2, x1. And this probability distribution of all 3 joint random variables, that's this filled in 2-simplex. This edge, the x1, x2 edge, that's right here. The x2, x0 edge, that's here. The x0, x1 edge, that's here. So this is a co-sheaf on this abstract simplicial complex. Of course, if I've got more random variables, no problem. I just keep building a larger simplex and build this out. Now, is this thing really, does this diagram commute? Yes, why? Famous theorem. Fubini's theorem, that's right. The statement that this diagram commutes is the Fubini theorem. If I integrate out this way, then the integrate along x2 and then x0, it's the same thing as integrating along x0 then x2. So the Fubini theorem is actually the key thing in proving that this thing really is a co-sheaf. Okay, that's pretty cool. And so you say, all right, that's marginalization. That's sort of something that comes along for free whenever I have a collection of joint random variables. What about if I'm kind of going the other way? If I talk about Bayes' rule, if you will, goes the other way. What does it do? It says that I'm starting out with a joint random variable distribution of n variables, and I'm going to push it up to a joint random variable with n plus 1 variables by way of some conditional probability. That's Bayes' rule. And of course, you could write this out very generally by using functions of various sorts like this. So
are you missing a vertical bar in your center SC or no? Is that truly a conditional?
C of xn given.
That's right. And in fact, I'm saying that this function here is in fact
I see.
Basically written
So
out.
you're saying it's something there.
It's something that
Turns
looks
out
very
that-
much like this.
Okay.
Absolutely. Yeah. So you're right. The typical notation for Bayes' rule uses this guy with the vertical bar saying all the things given over here and the thing that you've gotten over here.
Right.
Yes. But really, I mean, strictly speaking, this is just a function of n plus 1 variables.
But one is special.
Very special one, yes. Very special one indeed. So this gives me a way, if you look at the same space, what's going on here? It gives me a way to reverse, to go the opposite way. So the result is that when I specify Bayes' rule on a portion of these spaces of random variables that are sitting here, think of them as the stalks over this same simplex, it's defining a sheaf over a portion of it. You make that very concrete in a very small example. So here's 2 random variables. I've got a given conditional probability. Here the 2 random variables are x and y. They live over the simplicial complex from x to y. And so when I go from this simplicial complex from x to y, here we go. Here is the marginalization co-sheaf. In fact, this is the marginalization function. These are binary random variables. That is the marginalization function where I'm just integrating, of course, integrating summing here. And the conditional, on the other hand, what does it do? It takes me from given x, it tells me what the joint probability looks like. So it's a matrix, linear map, that basically multiplies out these various conditional probabilities. And if you notice, these are all the possible conditional probabilities you might need. So this particular construction is a paired sheaf, co-sheaf construction. And that gives rise to what a Bayes network is. Now you then might ask is, well, what is then a solution to a Bayes net? If I run this Bayes net, what do I get? Well, it's a section that is both a section of the sheaf and the co-sheaf. So it's this sort of joint section. I have to admit, this is something that is not really discussed extensively at all in the sheaf literature. In fact, I've really looked for this and haven't found it much at all. So I don't know a whole heck of a lot of this construction, but I have a funny suspicion that since we've got some now topological structure in the base, that it might be a very useful direction to study. To say, I've got some topological structure that is, maybe I'm not looking at a complete simplex, because I probably aren't. I mean, this is not a complete simplex here. Have some portion of that. Maybe I can use some information about, I know this probability distribution, I can push this direction in such a way that will then allow me to build the rest of the time. I don't know.
Michael, I think that what has happened is that people don't try to achieve a sheaf condition, but they start with some external data and they run these iterative algorithms,
Sure.
which are like local computations.
Absolutely.
They try to converge to a fixed point, which will be a section. I think that's what they're trying to do. But
Well, they typically are given a collection of margins.
Yeah, that
Yeah.
seems possible.
Yeah.
That seems possible. Yes?
And to clarify the way we have our four indices, it
Yep.
looks like the first index is P of x equals 0 and P of y equals 0.
Yep.
The second is 0, 1. The third
Yep.
is 1, 0.
And
the
the fourth is 1, 1.
Is-
Correct. Yep, you're absolutely right.
But typically you're given a collection of marginals and joints, and you're trying to, or sorry, marginals
Yeah.
and conditionals.
Yeah.
And you are trying to construct a joint.
Yes.
So.
In essence, what you're trying to do is you're trying to flow upstream.
And it tends to be under constraint.
Yes.
The joint tends to be under constraint.
That's right.
And then you need these iterated algorithms and things
That
like
you
that.
use these iterative
There's
algorithms
classes
to find
of
some
joints
kind
that
of.
are consistent with those and things like that.
Yes, so
In the real world, it's a much messier situation.
Absolutely.
There is a class of Bayesian algorithms that use junction trees, which look very much like some of the things you've shown here, where you
Mhm.
have these larger joint distributions or cliques
Sure.
that you operate against. So there's got to be a
Yeah.
strong connection.
Well, and there were discussions actually in the prior simplex meeting about also about factor graphs.
Absolutely.
As being a sort of
As being very related. Absolutely. So yeah, I think there are a lot of connections here, and there's a lot of good work that can be done to link up the more topologically minded viewpoint and a lot of the existing literature. Okay, cool. Any further questions or comments? Okay. So here's a very different picture of things. This is now belying some of my signal processing heritage. We're looking at filters from a topological standpoint. So asking the question, what is a filter and how does it work and how could I tweak it so that it can do more topologically useful things? So here's a simplicial complex model for a signal. And if I want a continuous signal, for instance, I build a simplicial complex for the real line. Imagine this is going on forever up and down. And I have then, sitting over every vertex and over every edge, some function space, collection of continuous functions. And sitting over this vertex is functions that are defined over an open neighborhood of that vertex. Here, these are functions defined between 0 and 1, and then et cetera. What does this mean? It means something kind of like this. It means that when I do restriction, I'm chopping the function in some fashion, chopping it down from a larger domain over that vertex to a smaller domain over the edge. And if I can paste all these things together, as in they agree, I end up with a continuous function. In some sense, this is the classical example of what a sheaf is. If you ask a mathematician, what's a good example of a sheaf, they'll say sheaf of continuous functions. This is, in fact, one way to do that. It's sort of a discrete version of that. Kind of handy. Now, what you might ask then is, well, what can I do with this sort of thing? Well, I don't ever work with continuous functions. I mess around with them and I shuttle them about. So let me tell you, how do I do that? How do I shuttle data around? Well, if I have data in this sheaf and data in this sheaf, I have to translate them. And the way to do that is to first ask on the level of topological spaces, or level, what do I do? Well, maybe I map this vertex to this vertex, these two edges to this edge, and that top vertex to the other top vertex. And what I do is I take the data in those various stalks and make some linear maps. Now, the strange thing about this is that even though the function on the level of topological spaces goes this way, on the level of data, it goes the other way. And this is something that is not at all obvious, but when you mess around with the various constraints, it turns out this is really the only way to do it. And so you end up specifying various linear maps to translate the data. This is just a notional example, so it's whatever happens to be built there. Now, it's a diagram being a homological algebraist, you look at this and you say, well, it must be a commutative diagram. So every square, every possible way to get from one place to another on this diagram, if I follow the matrices, it better commute, better get the same answer. Okay, cool. So that structure, map on the level of base spaces, and then data maps through the stalks in the opposite direction such that the resulting big diagram commutes, is a sheaf morphism. Now, why did I tell you sheaf morphisms? Well, because they do useful things. So if I have my sheaf of continuous functions here, and I'd like to discrete sample my data, this is something that people do in ADD converters in hardware, what I can do is I can imagine evaluating these continuous functions at specific points. And what am I doing? Well, I've got a map from my space of sampled data. Notice this is a flabby sheaf. This is not a flabby sheaf. At least not as flabby in any way. So the point being that, what am I doing here? This is a linear map that evaluates this function at 1. This is a linear map that evaluates the function at 0. And the diagram more or less obviously commutes because I got a lot of zeros in there. This is a morphism that samples this function. Now, when you sample data, you can end up with ambiguities, which is kind of neat or kind of bad, depending on your situation. So if I take a look at each of these functions this way, well, each of these are linear functions. I can ask for what is the kernel, or what is the set of elements here that got set to 0 here. Well, those are, in the case of this map here, I'm taking this whole thing to 0, so everything got set to 0, so that's the same space. Here, there's a little less that gets sent to 0. If you look at it graphically, they're the functions that will pass through 0 at the specified point. This seems kind of reasonable, and the result is, if you look at the sections of this sheaf, I call this the ambiguity sheaf, these are all functions that cross through 0 at all the integers. These are functions that if you were to sample them, what do you get? You get just a whole string of zeros. These are functions that if you add them to your data, sample it this way, you can't tell if you've added any of these functions on there. They're precisely the ambiguities of the sample. So that's kind of a useful way to think about sampling. Sampling picks up the data up to the ambiguities. So then any kind of restrictions in this sheaf that you can place, or constraints you can place on this sheaf, will result in fewer sections over in the ambiguity sheaf. Okay, that's kind of cool, kind of useful. And theorem, perfect reconstruction is possible only when I have no interesting global sections of the ambiguity sheaf. In some sense, perfect reconstruction is possible only when there are no ambiguities. This sounds like a Shannon-Nyquist theorem. In fact, you can prove the Shannon-Nyquist theorem through this language. In essence, what you do is you build, instead of a sheaf of continuous functions, you build a sheaf of band-limited functions, where essentially what we're doing is we just ask for these band-limited functions to be in the middle. That's the sheaf we're going to sample. And then we sample by way of an inverse Fourier transform. Standard way to do that. Sampling here at the integer n using the inverse Fourier transform. Notice I've got a band limit there. So go ahead and do that. I've turned this diagram on the side. So here's the sheaf of band-limited functions. Here's the sampled data that I'm pulling out of it. Notice the sections are complex numbers because I'm doing this all in Fourier transform land. That's fine. These are my inverse Fourier transforms pulling out the various values, and then I get some ambiguities over here. The ambiguities are, again, precisely the functions that vanish at all the integers. When you ask, all right, how many of them, given a particular band limit, well, it's standard manipulation that you can prove that that band limit is too small, you don't have any, which means, conversely, that if you sample at the right frequency with band-limited functions, you can do perfect reconstruction, standard stuff, but cast in the language of Sheaves. Now, why might you want to do this? You might want to do this if I've got some more complicated data space. Well, that's kind of interesting, and it leads to the question about filtering in general, because sampling is a kind of filtering. So, in fact, theorem, any discrete time linear translation invariant filter, standard sort of machine that people like to build in hardware, well, that can be encoded as a sequence of two sheaf morphisms, one that goes from the internal state to the output, and one that goes from the internal state to the input. Again, this is a question of the diagram, the arrows looking a little funny. You might think, well, gosh, those arrows ought to be going all this way. But in fact, what this is doing is think of these arrows as being data maps. They're projecting data out. Got more complicated, richer internal states, some of which projects out to give me the input, some of which projects out to give me the output. And in particular, the internal state is not entirely determined by any one given input. It's determined by some portion of the input. That internal state that I'm carrying around may in fact be something like a sliding window, or maybe something that's been preloaded into that filter. That'll give you the ability to manipulate what the filter's doing. In hardware, these are typically built that you've got an input buffer, an output buffer, some kind of shift register, and some kind of weighted sum or other nonlinear operation here. Fair enough. OK, so let me show you by construction how this thing works. So you start out with the input sheaf. Looks kind of like this. If you remember, this is actually a simplification of the Q example given in the previous lecture, where instead of continuous functions, we're looking at time series. And this is a flabby sheaf where I've got a real number at each time step. And on the intervening time steps, or on the intervening time, there's no constraints. So these are, what are the global sections of this sheaf? They're just real number sequences. Output, same thing, just real number sequences. The input, or the internal state rather, the internal state is this Q sheaf that we talked about last time. So this is a 3-deep Q, or a shift register. It's storing 3 numbers and shifting them along as we go. Again, its global sections are parameterized by sequences, but they're sequences that are grouped 3 at a time. So I have 3 real numbers here. I retain 2 of them and add 1 more on, retain 2 of them, add 1 more on, etc. Essentially, this is the contents of a sliding window. Now what I need to do is tie that sliding window to the input. Just project. So this will say, if I'm looking for a section that is valid over this portion of this sheaf, what I will end up with is I will end up with the third entry of each of these time steps Qs. The third entry is tied to the input, is exactly the input. Now what about the output? Well, some kind of function, linear function ought to translate these down. I could do something very simple and like weight them all the same. But I don't have to. I could weight them however I like or put some nonlinear function there or something. OK, great. So that's nearly everything. And then there's a bunch of zero maps that I need to put in there. And now this thing is a sheaf morphism, pair of sheaf morphisms. And there we are. And that's it. That's the construction. So that's kind of neat. Of course, that's kind of handy. And so, for example, you can look at the state of this filter at any given time. That's the state of the internal state. Notice how it ties to the input, and the average of 1, 1, and 9 is 3.7. Cool, OK. And of course, this extends. So that's kind of handy. Now, you might say, all right, why do this? I mean, it's a neat theorem. Totally neat theorem. But what it does for me is it allows me to, number one, splice in nonlinear operations. I didn't have to pick a linear operation. I would get not a sheaf of vector spaces anymore, a sheaf of something else. But that's fine. And it also allows me to play with non-trivial base spaces. And that's really very cool. So rather than asking for a sliding window that looks like a sliding window with time series, I can pick some more rich space there. And in particular, that's something I want to show you. So here's a very simple classical problem. I've got a noisy signal in blue. I'd like to filter out a signal in red. Of course, this is a sinusoid. This is a totally solved problem if I've got a sinusoid. Right? I mean, that's not hard. If I've got a chirp, so the frequency changes, and I use that same filter, that's obviously the wrong thing to do because it mangles my signal badly. So I do something like an adaptive filter. Those are great. And this is knowing exactly what the synchronization is. If I don't know the synchronization, I end up with trouble. I have to now track that chirp along. I don't necessarily know what that chirp is going to look like. I've got to retune my filter as it goes. And again, this is something people know how to do in some reasonable situations, but it's good to think about this in a little more general way. So let's see what we can do about this. Really, the problem is this. Here's the signal, and we're averaging along a contiguous sliding window. The problem is we're averaging some of the low values with the high values. What's the average of +1 and -1? It's not a less noisy estimate of +1. It's 0. And that's kind of bad. What you would really want to do is you'd really like to average all the +1s. and all the minus ones. Of course, the problem is that I don't necessarily know where the plus ones are. So what I need to do is I need to figure out where I need to be looking. If I can figure that out, then I can safely do a lot more averaging and come up with a better estimate. So here's sort of the idea. You take your noisy signal, you figure out where should I be sampling when. That turns out to be estimating a topological space. Very much like what we talked about in the second lecture, actually. And then once we've done that, that is the place that you want to build your internal state sheaf for your filter. Once you've got the internal state sheaf built over this space, now you can do your averaging passing through that topological filter, and you get a much better output. So roughly speaking, this is a caricature of what's going on, although this picture is true. Here's a function over two variables, and it's kind of periodic, kind of looks periodic. What you do is grab a neighborhood and slide that neighborhood all over this function, and grab some pixel neighborhood. I don't exactly remember how many points. It looks like I used a 4x4 grid of pixels and slid it around and looked at it, and asked that to be a vector in R16. These are the first two principal components, or three, I guess. What do you see? Well, for one thing, you see this sort of loopy structure. This has got some prominent loop in it. But we're not actually even going to leverage that. We're just going to leverage the fact that this distance matrix, telling me which points are where, telling me which points are nearby which other points, that particular metric space is going to work for my topological space. And I'm going to start building my sheaf over that using a Vietoris-Rips complex. When I do that, here's what I get. This is a distance matrix of sample to sample. This is now not over this picture, but rather over this picture here where I have a chirp. So this is sample number versus sample number. The diagonal, this is a distance matrix. The diagonal is 0. You can see that there's some periodic-like structure, but not completely, because a given sample, as you sweep through time, is similar to other samples. These low distance points are the points that you really want to be averaging with. So you build your topological space like that, aggregate your data into this sheaf. So now you're building the internal state sheaf built of neighbors in this topological space. This is what you end up seeing as your data. This is a particular section of that sheaf. And then we go ahead and average, pass it through that topological filter, and you get much better results. In particular, here's the output of that filter. You get extremely stable output. So you're able to really stabilize the output and get very good filtering. For comparison, here's a filter that has been synchronized and adaptively tuned to it. So you can see there's quite a bit of instability there. Yeah?
So what you described didn't seem to be, time varying or following the frequency. In other words, you took the data and then you...
That's right. This was all after the fact.
It's all after the fact.
That's right.
Whereas these other guys...
These other guys are streaming.
Right.
So you're right. There is a difference in algorithmic framework, and I won't claim that the comparison is 100% fair.
Well,
Sure.
In a lot of cases,
You have all the data. Yes, absolutely. Yeah, and in fact, the typical reason why I was going down this path is because I was using chirped sonar, where I had all the data stored anyway.
Yeah.
Seems kind of reasonable. Yeah, so in which case I could process the data at my leisure. Yeah. Now, this works. I did this on a one-dimensional example. This works very well on a two-dimensional example. Here, building adaptive filters is a much more dicey business. Here's a noisy input image. I'd like to denoise it. It's additive white Gaussian noise applied onto some quasi-periodic function. If you do something stupid like a fixed frequency filter, that doesn't work, obviously. But this topological filtering approach does a pretty decent job of cleaning it up. I actually have a hard time finding much of any visible noise in here. Of course, at this point, we should quantify performance. If you look at, since I've got the actual signal that went into this, I can measure the actual error as a function of noise. So as I crank up the noise, here's an SNR of 1. This blue is just a fixed frequency filter. Not necessarily the best choice, but certainly a reasonable choice if you don't have anything better. Using the topological filter and estimating the topology as I suggested, you get this green line. If you happen to know the topology outright, which is not quite as cheating as you might suspect, because I'm not knowing the synchronization or the timing, but I know that I'm looking for something that is perhaps periodic, or feels like it's periodic, it's a deformation of periodic, then I do a little bit better. So this quantifies the amount of topological estimation error that I've gotten. You can see it grows more or less linear with noise. And as you mess around with the filter sizes, you can see that it's basically similar linear progression. So this is not a bad filter at all. All right, so questions on this? Yeah?
So if you wanted to if you want to apply this technique to something that's being done on the fly,
Yeah.
what is hard about that?
So what is harder about that ends up being this topological estimation stage. Requires getting enough data that you can be reasonably certain that you've got the right topological space. And there are, the difficulty right now is actually the theoretical bounds versus the practical bounds on that problem are very, very different. In fact, the theoretical bounds are extremely loose. And the theory says that you need a heck of a lot more data and a lot cleaner data than what appears to be the case. They're almost always worst case bounds, and they're really bad. So understanding exactly how much you can rely on that performance is something that is really not very well understood. Other questions? Okay, well, that is all I have. So next up, next lecture tomorrow will be on some linear algebra and homological algebra and data types. That goes under the name of categorification, which is it's a mouthful, but it's a useful concept, and it turns out to be essential when we talk about heterogeneous data. The other observation is that there is an informal social down the street. We will happily welcome you all to. There are some references, and thank you.
Your references up there, understanding networks.
Yes.
Is that, are there applications?
Yes. Yes, in fact, that is much of the theory behind what I was presenting just now, on the filtering in particular. So we're looking at networks of signal processing architectures.
Just thinking of
Yeah.
things like social networks.
Ah, yeah. That is a good question.